This section is on line integrals, where instead of integrating over a one-dimensional interval, we're going to integrate over some general curve we'll call C. Now, before we begin examples, we'll go ahead and go over some definitions here. And the line integral over some curve C is, okay, we have this integral sign over C of f of x y ds, ds representing, we'll call it arc length, okay, with respect to t. Now, x and y, notice how x and y are functions of t, okay? Therefore, we'll integrate with respect to t or time, okay? And also, we can also parametrically define x of t and y of t as maybe some vector r of t, okay? And of course, this section here, this ds, we can think about it as the magnitude of the first derivative of r, okay? Now, going back to the definition of work here, work equals f dot d for displacement, force dot product with displacement. You might have seen this in a physics class. Okay. Now, also work can equal the line integral under the curve C of the force dotted with the tangent vector ds, where the tangent vector we'll define as, it's a unit vector, r prime of t over its magnitude. Okay, so there's that right there rewritten. And ds, we said, is this part, the magnitude of the first derivative of r. And it looks like algebraically these will cancel, and we're just left with r prime of t down here. The force dotted with r prime of t, and of course with respect to t. Okay, and we'll go ahead and look at another interpretation of a line integral, starting from this guy. We just rewrote it here, and we'll define f to have components, if it's in if we're working in R3, components p, q, and r. Okay, and you can do the dot product of r prime of t and f, and you get p dx plus q dy plus r dz. For these examples here, what I'm going to do is I'll go through all the vector calculus material and also the integration techniques, and as soon as we're integrating over polynomials, I'll just give you the answer from there. Okay, so for this first example, we're taking the line integral of y cubed ds, where the curve C is defined as x equals t cubed and y equals t, and t is ranged from 0 to 2. Okay, so now it looks like we can do a little bit of replacing here. Well, y cubed is t cubed, so we'll do the integral from t cubed, and ds being the arc length of this curve. Okay, and if you recall, the arc length is the square root of its differentials squared. Okay, so the derivative of t cubed is going to be a 3t squared, I suppose, and this will be squared, plus, and then the differential of y is going to be just 1, and we'll have a 1 squared here, and we'll integrate with respect to t, and it looks like t is ranged from 0 to 2, meaning we're integrating this integral from 0 to 2. Okay, let's go through the arithmetic. We'll have a t cubed square root of, looks like a 9t to the 4th plus 1 dt. And it looks like if you look at the integration techniques used here, we'll have u equal the inside function, 9t to the 4th plus 1. So du is 36t cubed dt. So dt equals du over 36t cubed. Scrolling down here. And this t cubed here will cancel each other out. I'll have a 1 over 36 out front. Integral from 0 to 2 of root u du. And I'll stop there. Oh, actually, I made a mistake. We should have our bounds changed. When t is 0, it looks like u is going to be 1. And when t is 2, oh boy, let me get my calculator really quick. T to the 4th times 9 plus 1, 145 up here. Okay. And it looks like this is easy enough. We'll stop here and I'll give you the answer. And I have 145 times root 145 minus 1 all over 54. Okay, and now for the second example, the line integral of x times y to the 4th ds, where the curve C is the right half of a circle, x squared plus y squared equals 16. So I guess this curve C here is a circle of radius 4 centered about the origin. Let's go ahead and draw this and just get a geometric interpretation. Don't need to be too fancy here. But here's the right half of a circle, and you should have been born knowing the equation or the parametric equation to this circle. We'll call it r of t equals, should be 4 cosine t, 4 sine t. And it looks like t is a parameter representing angle, and I guess t is ranging from negative pi over 2 to pi over 2. And I'll go ahead and write that out. T ranges from negative pi over 2 to pi over 2. Okay. Now, we'll go ahead and do some replacement here. X is a function of t, and that's a 4 cosine t, multiplied by y, which is, I guess, a 4 sine t, and we'll raise it to a 4th power. Okay, and then ds represents arc length here, and we'll go ahead and take a differential of 4 cosine t and square it. So we'll get I guess that's a negative 4 sine t. We'll square that. Plus the derivative of 4 sine t will be a 4 cosine t. Square that. And integrate with respect to t. Oh, and t ranges from negative pi over 2 to pi over 2. Okay. Now notice how this is symmetric here. So I'm going to go ahead and multiply the integral by a factor of 2. And the consequence of that will be, we'll go from 0 to pi over 2 instead. Okay. We have 4 times a 4 to the 4th, which is 4 to the 5th. Okay. Times cosine t sine to the 4th t. Those are multiplied together. Times, okay, we have a 16 sine squared plus a 16 cosine squared dt. Okay. And notice how if we factor out 16 inside the square root function, we'll have a sine squared plus a cosine squared, and you should know that should be a big fat 1. So we end up with just the square root of 16 here, which is 4. So I'm going to go ahead and erase this. So we'll get another factor of 4. 4 to the 6th this time, times the integral from 0 to pi over 2 of cos t sine to the 4th t dt. Okay, this calls for a u substitution. We'll let u equal sine t, so du is cosine t dt. So this factor of cosine will, or 1 over cosine, will cancel out this cosine here. Okay, we'll get 2 times 4 to the 6th, the integral from, well, when sine is 0, u is 0. When sine is pi over 2, u is 1, of just u to the 4th du. I'll stop here and give you guys the answer, and you should have 4, oh, it looks like a 4 to the 5th multiplied by 2 all over 5 is what you should get. Sorry, I think I made a computational mistake here, but my answer should be 4 to the 6th times 2 over 5. Okay, next is a line integral, another line integral represented in a different way. Okay, looks like this is the integral p dx plus q dy plus r dz. Okay, we're doing a line integral in R3 this time. And well, let's read it out. Z squared dx plus x squared dy plus y squared dz. And C is a curve represented by a line segment from the point 1, 0, 0 to 4, 1, 2. Okay, so the question is, how do we represent this curve parametrically? Well, let's go over that really quick. If you recall, the parametric equation, or general parametric equation, you start at some point and we'll add some scalar multiple of some vector. Okay, so, and it looks like, I guess v in this case is going to be the difference of, the difference of these two points, these two vectors. So we'll have the vector 4, 1, 2 minus 1, 0, 0. Okay, and I guess we get 4 minus 1 is 3, 1 minus 0 is 1, 2 minus 0 is 2. Okay, there's that vector there. Okay, and P naught it starts at 1, 0, 0, it says, so I guess R of t should be the vector 1, 0, 0 plus t times v, which is 3, 1, 2. Okay, and adding these two vectors together we'll get a 1 plus 3t, 1 and, 1t and 2t. So now if we want to represent this vector equation going from the point 1, 0, 0 to 4, 1, 2, I suppose t needs to range from 0 to 1, because when t is 0, we get the point 1, 0, 0, and when t equals 1, we get the point 4, 1, 2. Looks like we're ready to compute our line integral. Okay. We'll take an integral from 0 to 1 of z squared dx. Looks like z is 2t, so we'll have a 2t squared multiplied by dx, the differential of this x here with variable t will just be a 3 dt plus x squared being 1 plus 3t, 1 plus 3t. We're going to square that, and then a dy will just be a 1 dt plus y squared, which is t squared, denoted here, and then a dz will be a 2 dt multiplied by 2 dt. Notice how all three of these terms have a dt, so I can just factor out that dt on the outside. We're still left with the integral from 0 to 1 of, let's say, a 4t squared, times 3, which will be a 12t squared, plus 1 plus 3t squared will be a 1 plus 6t plus 9t squared. Okay, and then plus 2t squared, Factoring out the dt's, I'll go ahead and combine like terms. So a 12 plus 9 is a 21, plus 2 is a 23t squared. Is that right? Yes, 23t squared plus 6t plus 1 with respect to t. Oh, that should be a dt. And this is pretty simple from here. This is just calculus 1, and you should get a 35 over 3. Thank you for watching. Hope you learned a lot about line integrals. There will be a second part of line integrals here, and please subscribe and have a good day.